In this example problem, there is a magnetic circuit, and it is a magnetic circuit of a shape that is a torus. So basically, what a torus is like a donut shape. So a toroidal shape. It looks like this. So instead of our circuit being square, it kind of looks like this. And let's see, it has an inner radius and an outer radius. So that's implying to me that the cross section of this toroidal shape would be round. I mean, you could make a toroidal shape that has a rectangular cross section or a square cross section, but I'm assuming since it says inner radius and outer radius that this is a circular cross-sectional toroidal shape, kind of like donut. Oh, and it says here, it's a donut-shaped core. And it's asking us to calculate the reluctance. Reluctance, if I just remind myself, I draw it like this, Rm. The units of reluctance are amps times the unofficial unit of turns over the Weber's, the number of magnetic flux lines in it, or of course that's a 1 over Henry. So I need to calculate the reluctance. It's made out of low carbon steel. Low carbon steel would sort of tell me that's like a material property, right? So low carbon steel, it must be a material. That material must have its own permeability. Sure enough, it does have a permeability mentioned in the problem here. It looks like it's 2 times 10 to the negative 4 Weber per amp turn meters. So that it's low carbon steel has this permeability. That's what the low carbon steel meant. It has an inner radius that is known and an outer radius is known. So I know its shape. And that's the question. Calculate the reluctance. That's the question. Now this is an answer, but I'm going to do an answer as well. All right. So the question is, so I'm going to do my own solution and kind of walk through it. So solution. The question is, please calculate the reluctance. So I would always start with what I am supposed to solve. Reluctance, what do I know about reluctance? I know that it is the magnetic motive force over the number of lines of flux that got established. That's a definition of reluctance. And another definition of reluctance is 1 over permeability times the length over the area that we're looking at. So if I look at these two definitions of reluctance and I say, do I know FM? FM is the amps times the number of turns. I don't know the number of turns. I don't know the number of amps. And I don't know a count of how many flux lines. So I think this is actually not very useful to me. I suppose it can stay there. I don't mean to say that it's an error, but it's not very useful to me. Whereas I look at the other definition of reluctance and I know the number 1, I know the permeability, I know geometry, and I know geometry. So I'm going to do this one. Now, what do we have to find out? We know, let's see, well, I can already sub in. So where permeability equals 2 times 10 to the negative 4 Weber per amp turn meters, and where L equals length, and where A equals cross-sectional area. Equals cross-sectional area. So what we're going to have to do is figure out then what is length and what is cross-sectional area. These are going to be our important things to have to figure out in order to sub in. So let's do length first. Let's find length. What does length mean? L, it actually means the mean path length. L is the mean path length, which is mean, kind of like average, right? Path length. what this is saying is that it is the average, basically, the average of the paths that the magnetic lines of force travel through. So if this is the path, that these magnetic flux lines travel, we like to do our magnetic flux lines in blue, then some of these magnetic flux lines travel on the outer path. These magnetic flux lines, some of them travel on the outer path. Some of them travel on the inner path. What would be the mean path? The mean path would be the path in the middle. The mean path length, L, is the path in the middle. So I'm going to say mean path length is the same as average path length in meters. It's the average length that the flux lines are traveling. It's the average length the flux lines travel in meters. In the average length that these flux lines travel are right here. It's the middle. So then it's going to be the circumference of the middle for this question. Circumference of the middle of this donut. For this question. So therefore, it is the circumference. What would that? I can actually calculate what that is because I know what the small path length is and I know what the large path length is. I have that written down. So it looks like, given the geometry of the question, the geometry is given in the question. So I'm going to have to put that geometry on. The geometry in the question said that the radius to the outer surface, it's 225, let me see, 2.25 centimeters, 2.25 centimeters in meters. So our outer is equal to 0.0225 meters. And our inner is equal to 0.0175 meters because it was 1.75. And now I can readily calculate what this would be to the radius that I care about. The radius I care about is this one in the middle. And that would be the radius to the middle, right? Radius to the middle. There's a few different ways to do this. And if I have the radius, I can calculate circumference because circumference is 2 pi times radius. We might have forgotten that, but circumference is 2 pi times radius, or it's pi d. But now there's a couple of ways to do this. Some people go, our outer minus our inner divided by 2. That's one way to do it. Or you can calculate what is the difference here. You can say 0.0225 minus 0.175, and then divide that in half to get half of this and add it to the inner one. But I think most people probably add the 2 and then divide in half. So basically I have to find our middle. So I'm going to do it, I'll just do it one way and take the average of these radiuses. So I'm going to go outer 0.0225 meters plus inner 0.0175 meters. It's not intuitively the way that I would approach this problem, but I find that, a lot of students do like approaching a radius this way, and I would divide that in half. And I would get the fact that the radius to that middle or to that mean path length is, let's see, what is it going to be? It's going to be 0.02. 0. I'm going to keep a significant digit there because I'm dealing with real measurements. 0.020, and I should keep 2 significant digits, actually. I should keep 4 significant digits. Okay, so that is my radius to the middle. So my mean path length, back to my mean path length, would be pi d. So pi times 2 of those, or 2 pi radius to middle, which would be 2 times pi times 0.0200 meters. So what that gives me is a length or a circumference of 0.1250 meters. So I'm just going to put that as a therefore statement. Therefore, L, which equals mean path length, equals 0.0200 meters. Now I know one, I know permeability, I know length. Now I need area. So now we have to really know, what does area mean? What does area mean in these formulas? Because we know these formulas, but we don't know them practically yet. We don't know them practically well enough yet. So we have to realize that area means cross-sectional area. And that's a really big takeaway from today, is that area means cross-sectional area. So let me just try to get this mean path length back up here. Oops. Let's put this mean path length where it ought to be. And let's remind ourselves of what we're looking for in this question. Let's just remind ourselves, since we're on another page here, that we are looking, remember, we are finding reluctance, and it is equal to 1 over permeability times length over area. We have 1, we have permeability, we have length, we need to find area. So let's find area. And at the same time, let's define what this area means. A equals area equals, what it is it's a cross-sectional area. And that's really, really important, that it's a cross-sectional area. If we draw this again, if we draw this toroidal shaped magnetic circuit, this is the entire magnetic circuit. This magnetic circuit has flux established inside it. Lines of flux are established inside this magnetic circuit. Great. But the area, and it's a toroidal shape or a donut shape. So right now I'm looking down at this donut on my plate, and it has these magnetic lines of flux moving through it. But that's not what cross-sectional area is. Sure, we have some dimensions for that, but that's not what cross-sectional area is. It's a cross-sectional area. It means that we have to take a slice out of this donut, or let's say it's like more like a bundt cake, if we know what bundt cakes are. And we have to take a slice of it, and we have to say, I'm going to share this with my friends. If I were to share this donut with my friends, I would slice it here and here and here and here and here and here. And each friend is going to have a section that is sliced. It's sliced where I just cut it with a knife. And if I were to take one of those slice lines, look at the slice. Look at the slice, and then look at the slice from the angle, then this is a cross-sectional area. Okay? This is a cross-sectional area. We do not take the geometry of that whole donut. We do not take the geometry of that whole toroid. We take the A means the cross-sectional area. If I were to draw the lines of flux in this cross-sectional area, they would look like this. They would look like this. They're coming out of the page or they're going into the page. So flux comes out of page. Kind of like when we calculate magnetic flux density, they come out of the page. Now, we already had some geometry. From the question, we knew this and we knew this geometry. I think this was 0.0225 meters. And the inner radius, I believe, was 0.0175 meters. In magnetic circuits, in these formulas, we want to work in our base SI units just to make everything simple. Convert your problems to their base SI units would be very helpful to you. So if I were to look at how big this cross section is, then I would tend to think it's from the outer side of my toroid to my inner side of my toroid. So I would say that the length across here, which would be my my diameter here. This is the diameter, right? Diameter of cross-sectional area. I like to write cross-sectional area A pi. That's just what I like to do because it's a plane. So A perpendicular cross-sectional area, or I could put a pi there, the area of the plane. Sometimes pi is a short form, sometimes perpendicular. I'm saying it's perpendicular to the toroid. So the area there then, so the diameter of this perpendicular area or diameter of this plane is going to be, it's going to be the outer radius minus the inner radius. R outer minus R inner of my toroid, which was specified in the question. 0.0225 meters minus 0.0175 meters would give me the distance across this cross section, yes? So that would be 0.005, and I like to keep 4 significant digits, which we can talk about at some point. That's the diameter, but we don't want the diameter. We want the area. We want the area of this cross section. It is perpendicular to our toroid. A of my plane or my cross-sectional area is going to be equal to pi r squared. It's just the formula for area, right? Area equals pi r squared. So we are remembering back to our area formula. We had to remember back to our circumference formula in order to do the mean path length. So this is going to be pi. I know the diameter. I just calculated it down here. 0.0050 meters. That's going to be squared. It's going to be squared. I have to divide it by 2 because I want radius. This is all going to be squared and the meters are going to be squared. So we have to make sure that we, square this properly and that the 2 is also squared, right? Because it's the diameter is divided by 2, and then the diameter is the radius divided by 2, and then all of that gets squared. 1.96. times 10 to the negative 5 meters squared is the cross-sectional area, which makes sense because it's in meters. And this number seems in line for what we need. All right, so then now I have everything I need in order to sub into what I wanted to find in the first place. So I'm just going to put a little cross this out, and I'm going to keep using this piece of paper. If I remember back to the initial question asked, find the reluctance. Find the reluctance of this toroid. So we had this toroid, and of course, it's either permeable or reluctant. It is reluctant to establish some magnetic flux, and we want to find how reluctant is it. Well, here's how reluctant it is in establishing its magnetic flux. We know that relationship relates to the permeability of the material normalized by length over area. We know that permeability was given in the question. We know that mean path length is the middle path length that these lines of flux traveled, and we calculated it. We know cross-sectional area is the area of this plane that I took off, and that's cross-sectional area, and we calculated it. And now, so we just have to plug it all in. We just have to plug it all in. So it is on the numerator would be our mean path length, which is just in meters. In the denominator, we have 2 times 10 to the negative 4, which was our permeability. I like to keep T in there for amp turns. We have our cross-sectional area we calculated above, 1.96 times 10 to the negative 5 meters squared. We're going to make sure that we are doing very nice math by keeping all of our units so that we can cross them out. Well, this meter squared is going to get crossed out by this meter, which is in the denominator of the denominator. So now I just have 1 meter here. And then that meter is going to get crossed out by this meter. So we want to keep all of these units so that we do a very good job of not having any inaccuracies in our math. If we were to calculate this, we would get 31 point, I want to keep another decimal place, and I don't quite have it, but I'm going to put 90 times 10 to the 6 amp turns per Weber. And that's the answer to the question. Therefore, the reluctance of this circuit is 31.9 times 10 to the 6 amps per Weber that's trying to get through it. And that is our answer. So in this question, we had to know the formula for reluctance. We had to know it relates to permeability, which was given. We had to find the mean path length and the cross-sectional area, remembering the mean path length and cross-sectional area, what their definitions are. That is not the area of the toroid that was given in the question. It's a cross-sectional area if you were to cut that toroid. And length is not the outer length, it's not the inner length, it's the mean path length that the average of all of those magnetic flux lines would be traveling.